our next topic is continuous charge distribution. In continuous charge distribution, we have to learn three types. The first one is line charge distribution. Suppose a charge is distributed over a line, like a conducting wire. This is a line of length L. Okay. Now charge is distributed over it, let us say uniformly, or may not be uniformly. Take a small length dl of it. On this length dl, let the charge be dq. Then the linear charge density, also known as charge per unit length, is represented by lambda. It will be charge on length dl is dq, therefore charge per unit length will be dq by dl. This is called linear charge density. Linear charge density. Its SI unit will be coulomb per meter. Dimensional formula you may write down yourself. Okay. Now, due to this line charge distribution, we want to find the intensity of electric field at a point P, which is at a distance r from this element of length dl. Now, if I place a test charge Q0 here, the force experienced by that Q0 due to this element will be dF will be K. You all know what is K. K is 1 by 4 pi epsilon naught. K Q0 dq upon r squared, unit vector r cap. Do you agree? Charge Q0 into charge of this small element, which is dq. But what is dq? From this relation, it is lambda dl. Therefore, what do we have here? It will be K Q0 lambda dl r cap upon r square. This is the force experienced by charge Q0 placed at this point P due to this element alone. Now, what will be the total force experienced by this charge Q0 due to this entire length of this element F? It will be line integral dF. What do you mean by that? You divide this entire length into small elements of dl. Find the force acting on Q0 due to each of them and then sum them up. That is line integral dF. Okay. So, what do we get here? We are going to take integral of this. Integral of this, you can take out the constants. What are the constants here? Q0, K, lambda. Lambda may not be constant, it may vary from place to place. The linear charge density may be different at different places. Therefore, Q0, K is 1 by 4 pi epsilon naught into lambda dl upon r squared, unit vector r cap, line integral. What will be intensity of electric field at this point due to this entire linear charge distribution? E, what is that going to be equal to? F upon Q0. If you divide this by Q0, what do we get? We get K line integral lambda dl r cap upon r squared, line integral. I am putting the value of K. What is that? 1 by 4 pi epsilon naught, line integral lambda dl r cap upon r square. So we got expression for intensity of electric field at a point near a linear charge distribution. Now we will discuss about surface charge distribution. To surface. Earlier case we discussed was line charge distribution or linear charge distribution. That was in one dimension. Now surface charge distribution is in two dimension. Here is a surface with charge distributed over it. Let the surface be S. Take a small element of surface here. Its surface is ds. Surface area is ds. And the charge on it is dq. Then the charge per unit area, or called surface charge density, symbol is sigma. Charge per unit area will be dq upon ds. Its unit will be coulomb per meter square. Now, due to this element alone, I want to find electric field intensity at this point P, which is at a distance r from this small surface element ds. What will be the force exerted on a test charge? Positive test charge Q naught placed there. F will be equal to K Q naught dq upon r squared unit vector r cap. But from this relation, what is dq? It is sigma ds. For this I can write as K Q naught sigma ds upon r squared unit vector r cap. Now the force experienced by this test charge placed here due to this entire surface will be, this was df, sorry, okay. F will be equal to surface integral df. What do you mean by surface integral df? You are going to divide this entire surface into small elements of area ds. Find the force acting on this charge Q naught due to each of these elements and sum them up vectorly. And so what do we get here? Integral K Q naught sigma ds upon r squared surface integral unit vector r cap, taking out the constants, K Q naught surface integral sigma ds by r squared unit vector r cap. This gives you force exerted on test charge Q naught placed here due to this entire surface. What will be intensity of electric field at that point due to this entire surface? It will be F upon Q naught, force experienced by unit positive charge placed here. Dividing this by Q naught, what do I get? K surface integral sigma ds by r squared unit vector r cap. What is K? 1 by 4 pi epsilon naught surface integral sigma ds by r squared unit vector r cap. So we learned surface charge distribution also. The symbol for charge per units of area is sigma and its unit is coulomb per meter squared. Now the third charge distribution, that is volume charge distribution. This is in two dimension. The earlier one was in one dimension. Now the third one, volume charge distribution, will be in three dimension. volume charge distribution. Here is a solid in 3 dimension in which charge is distributed in 3D over the entire volume of that body. Let the volume of this be V. Take a small volume inside and taking in the shape of a cube. Its volume is dV, and the charge in that volume alone is dq. Then volume charge density, that is charge per unit volume, symbol is rho, will be dq by dV. Now I want to find the intensity of electric field at this point P, which is at a distance r from this element alone of volume dV. The force experienced by positive test charge plays. A positive test charge means a very small test charge. Positive test charge plays Q naught. Force experienced by it due to this element alone will be dF will be equal to K Q naught dq upon r squared unit vector r cap. What is dq from this relation? It is rho dV. For K Q naught rho dV upon r squared unit vector r cap. Therefore, what will be the total force experienced by this due to this entire volume? It will be integral dF. What integral? Volume integral. dF. What is that? I am directly jumping a step, taking out the constant terms. K naught volume integral rho dV by r squared unit vector r cap. Now this is the force experienced by charge Q naught placed here due to this entire volume. But I want intensity of electric field. That means force experienced by unit positive charge placed here. That will be this force divided by charge. Therefore, E, intensity of electric field there, will be equal to F upon Q naught. Dividing this by Q naught, what do I get? K volume integral rho dV by r squared unit vector r cap. What is K? 1 by 4 pi epsilon naught volume integral rho dV by r squared unit vector r cap. Okay. Integral, you have learnt in 11th standard, the symbol of integration and what is integral. Integration.